Hello and welcome to Empowered Learning. This is the second video in the video series explaining spring mass systems, and particularly modeling them with second order linear, homogeneous, and non-homogeneous equations where all the coefficients are constant. So this video we will go into a deeper dive into the case 1 case, the underdamped or no damped case, and no damped case, I should say, for these types of systems. And we're going to talk about the concept of resonance. So that's the main focus for this particular video. If you're interested in just hearing about the theory, then you need to watch part 1 of the first video. If you're just interested in kind of seeing, well, how do the problems work, then you need to look at the part 3 video. So this video, again, will strictly talk about the case 1, and I'm going to throw in there a little bit about case 2, but essentially it's going to be the case 1 situation and how that case actually helps us to be able to see and experience this phenomenon called resonance. So I wanted to start off by just recapping on what those 4 major cases are for these types of equations. So we have case 1, and a case 1 is essentially no dampening whatsoever. So our damping coefficient for our dashpot or shock absorber in our spring mass system is 0. When we have that type situation, our response is very much oscillatory. So it looks something like this. I usually write cosine first, but I'll just do sine first here, just because that's what I was thinking about. So our system looks like this. In a case 2 type situation, we do have some dampening, but the dampening is a value that is in between 0 and this quantity here, which is 2 times square root of the product of the mass and the spring constant kappa. Okay? And so when we have this situation, what we end up with is a situation that looks like this response-wise. And again, since I wrote sine first, I'll keep it looking that way. And remember here that because we have this exponentially decreasing portion of our response that's being multiplied times it, that is what's making our system response, the oscillations that occur, meaning the mass moving back and forth, is going to eventually decay away and get back to equilibrium position. Okay, so of course case 1 is just oscillating the same forever and ever. Case 2 is going to oscillate, but over time it's just going to die out. Okay, but it still takes it a while to do so. Our case 3 will be the situation where we call it critically damped, where the thickness of the material or fluid or whatever is in our shock absorber, aka the dashpot, it's such that it makes the discriminant for the roots of our characteristic equation for where these responses come from, makes that go to 0. And what we essentially have is a response that is switching over from being oscillatory to exponential. So I'll write it this way. Okay. And again, I'm switching it up. I usually put the T with the C2, but since I switched up sine and cosine here, I normally put cosine here, sine there. Since I switched it up, then of course this needs to switch as well. Now case 4 is a case where everything is purely exponential at that point. And we know that our damping coefficient is going to be greater than 2 times the product of mass times spring constant. And in this case, what we end up having is something that's purely exponential, and that is going to look like this. Okay. And I'm assuming in this case here, in the way that I'm writing it, that my R1 and R2 are going to be greater than 0. But in actuality, if I did not write the sign there, we know that the roots from our characteristic equation will always produce values of R that will end up being negative for these type systems. Okay. And so it's important to know that these roots will be negative, because if they're not, then what we're going to be having is a sum of exponentially increasing functions, which kind of grows out of control. Okay? So whenever our roots are both negative, what we essentially have is an exponential response that looks like this. If we have a situation where our roots are greater than 0, or at least one of them ends up being that, you'll have a situation where it may do this, but it eventually goes up like this. And that's going to be a problem for a spring mass system, because if we allow that to happen, then it goes against some of the assumptions that we made in the part 1 video, most of which is the spring in our spring mass system follows Hooke's law. And we know Hooke's law, again, is just going to be F is equal to K times Y. And since that force is acting opposite of any external force that would be on the system, then the equation would look like this. And this equation is only valid if we don't stretch or compress the spring too much. Okay? By us having a response to where these R's would be positive, would essentially make us have a situation where we're stretching our spring too much. Also stressing out our dash pot or shock absorber as well. And before we even get to, astronomical values, either the spring or the dash pot will break. Okay, so we got to keep all those assumptions in there just to make sure everything works out fine. Now, I wanted to kind of do a summary of what these responses are, because we're going to focus on case 1 here. So this case 1 is very, very important in the topic that we're going to talk about today, which is called resonance. And so notice that in case 1, we see that our response is purely oscillatory, and it never dies out. So since it is oscillatory and it never dies out, one of the things that we want to study is, well, what would happen if we applied an external force to this system in this state where the oscillations of the mass going back and forth will never die out? Is there ever going to be a situation where we can apply a force that could possibly make that particular system oscillate out of control, or at least oscillate much more than what it normally would, displacement wise, from equilibrium, based upon what type of external force we have? And the answer to that is yes. And the only time that that would actually happen is in a case 1 situation, where we essentially have no dampening, and if all things being confined within the spring mass system, it just oscillates forever. If I apply something to it, depending upon the properties of that force, it can make this thing oscillate much, much higher than what it normally would, or it can make it oscillate out of control. And so that's what we want to talk about. Before we get into that, we need to define a few things as far as what our responses for these types of spring mass systems and the corresponding theory for the equations, the responses for those equations that we use to model these spring mass systems. We need to identify some things vocabulary-wise, so that when we're talking about what the definition of resonance is, we have a clear understanding of that. So when we talk about spring mass systems, there are two primary responses that we are concerned about. So these responses are called a transient response. It's better known as a impulse response. I think in the part 1 video, I called this the response where we had a quick burst of force or energy. So that's essentially what a transient response is. And the steady state response. The steady state response, you can think of this as how is our spring mass system going to act as time approaches infinity, as it goes on forever and ever and ever. Okay? Are things going to settle and balance out, or are they going to still be oscillating, or what? So that's what the steady state response is. Now, in terms of what we know about second order linear homogeneous equations or second order linear non-homogeneous equations, one of the things that we learned is that our response to those types of equations, in particularly the non-homogeneous ones, is a sum of homogeneous and particular solutions. And so whenever we talk about a homogeneous solution in terms of spring mass systems, we're talking about the impulse or the transient response. For spring mass systems, when we say a steady state response, what that really is in terms of differential equation theory is the particular solution. Okay? So just think about it this way. The particular solution or the steady state response is going to be the response that happens as time goes on forever and ever. The homogeneous is going to be what happens if we have some kind of short-term initial burst of energy or force that's applied to the actual system. How's it going to act for those kinds that are relatively close to zero? Okay? So now that we've taken the time to actually define what a transient response is, what a steady state response is, we're actually going to go over the definition of resonance, and then I'm going to go through an example with you to try to illustrate that. So our definition of resonance is we're going to have at least one oscillation or vibration that occurs in our system that's going to be larger than normal amplitude-wise, and that occurs when we have some kind of external oscillatory force that is applied to the spring mass system. That force has a frequency that is close to or equals the force of the natural frequency of the spring mass system. Remember the omega naught or omega that we talked about in the previous video. And the amplitude of that oscillatory force function is relatively small compared to the larger than normal amplitude response of the spring mass system. Okay, so I'll read through that again, and then I'll show you an example of how this would actually look from a function perspective. So resonance is at least one oscillation or vibration of larger than normal amplitude that comes out as a result of some forced function on the spring mass system, or some force on the spring mass system that's external to the system. And we know that that particular force, it has a frequency that is either close to or equals that of the natural frequency of the spring mass system, or whatever omega is for the case 1 spring mass system response case. And the amplitude of the oscillatory force function being applied to the system is relatively small compared to the response that we get. So basically we put in a little thing, we get out a huge thing. Okay. Now, to sort of illustrate how this would work, I'm going to show you the result of 2 examples I'm actually going to do in the part 3 video, but I'm going to show you the functions for it
to kind of give you an idea of why this is actually happening. And then I'll show you an example graph-wise of what this may look like. So one of the things that we are going to see in the examples I'm going to do in the part 3 video is that we're going to see what happens when we take our spring mass system with some things constant about it. So let's say our mass is going to be 12 kilograms. We're also going to know that our spring constant here is also going to be 12. Okay. And if I remember the units right, that's going to be 12 kgs per second squared, or kilograms per second squared. So if we have that going on, then we'll see that if I was to apply an external force of 24 newtons, just constant 24 newtons, we would see that the corresponding response to that system with these conditions here and our dampening being non-existent, because that's what case 1 is when the dampening is 0, we'll see that we end up with this oscillatory function, of course, some constant times cosine plus another constant times sine plus 2, okay? And so this 2 here, in the grand scheme of things of our actual response being the homogeneous plus the particular portion, this is going to be the particular portion, okay? Now, we see here that if I was to try to figure out, well, how high is this going to go? Or how low is it going to go? Or put another way, what's going to be the amplitude of this particular function here? Well, it turns out that we could rewrite the C1 plus cosine of t plus C2 sine of t as just some amplitude, and I'll call it C, times either a cosine function or a sine function. Now I'm going to skip all the particulars on this, but I am going to write out what this possible response could be, just so that you can see what I'm talking about as far as amplitude is concerned. So I'm going to erase this for a second. And just know that what I'm about to write actually comes from your pre-cal or trigonometry courses. You may have taken or learned this in a pure trigonometry course, or may have been a part of a pre-cal course, but it'll be the trigonometric portion of it. So in short here, and again, I'm just talking about this response, I could rewrite this in one or two ways. I could rewrite it this way as C times cosine of t minus phi, or I could write it as C times sine of t plus alpha. And C ends up being the square root of C1 squared plus C2 squared. Of course, those are just my arbitrary constants that are there. My angle phi that's here, most people express this as tangent inverse of C2 over C1. I'm not going to do that, just because it really does depend upon what quadrant you're in. So what I'm going to do instead is express it in a way to where we still have to figure out what quadrant our angle phi or phi would be in before we make the final assumptions here. So I'm going to express it this way. And of course, depending upon whether C1 or C2 are negative or not, or both being negative or both not being negative, that will let you know what the phase angle phi or phi, depending upon how you pronounce that, will be. So our angle alpha here, if you wanted to express it as a sine function, would literally just be pi over 2 minus whatever phi is. Okay? The point that I want to make is that for this portion, we know that the amplitude is going to be c. And if we have plus 2 on that, then of course the magnitude, or as I'll say the amplitude of this particular function, on the high end, it's going to go to c plus 2. On the low end, it's going to be c minus 2. Okay? Or really, let me rewrite that. It's going to be minus c plus 2. Okay. So it'd be like that. So the main point that I want to get across here is for this first function, if I was to try to see, well, how is that going to act as t approaches infinity, all I know is that the function will oscillate, and it's going to oscillate in between 2 plus c and 2 minus c. Okay, so it may start here, but it's basically going to act like this, and it'll keep on doing it forever and ever and ever. In the case of this response, where we add an oscillatory external force to our system, and the frequency at which this particular function oscillates, and since this is sine t, we know we have an understood 1 in there, and of course from an angular frequency perspective, it's going to be 1 radian per second. And notice that we have, for the homogeneous portion of this particular response, we still have the same 1s in there. Okay, so what that's telling us is that the homogeneous solution and the particular solution for this second response, these two responses, both the external force and the homogeneous or natural response for our spring mass system, are both oscillating at the same frequency. Okay, and so what that's going to end up having is a compound effect on the spring mass system. Now, using the same kind of knowledge I just talked about here, and I'll name this Y1 and Y2 just to give a clear distinction in between the two. So this is the response for Y sub 1t. Then a response of Y sub 2t. Notice that what it will do is, again, it's going to have a response of, it's going to bounce in between minus c and plus c if we ignore this portion. But because of the fact that we also have to add on this negative 6t times cosine t, we know that on the high end, this is going to be a case where we have a positive 6t, and on the low end, it's going to be a minus 6t. The issue here is that t is approaching infinity. And as t gets larger, the actual amplitude gets larger. So what you end up with is a system that starts to respond like this, and then it just gets bigger and bigger and bigger and bigger, because, again, t is getting bigger and bigger and bigger and bigger. And of course, if you look at this, you'll see that the oscillatory motion is increasing in a linear manner. And that is because of the t part of this particular term. And so this specifically happens at a maximum whenever we have a situation where we have an external force that is applied to a spring mass system. It has the same frequency as the natural or the homogeneous response, to it. And we see that 12 is the amplitude for that. But notice that after about 2 seconds, we're going to pass up an amplitude of 12 real quick. And there's no way to stop this. Okay? And in actuality, this is what resonance actually looks like from a mathematical and graphical standpoint. We see that as t goes to infinity, of course, the function goes out of control. And from a practical standpoint, what would actually end up happening is that our spring or our dash pot, or both of them, would actually break. Okay, and thus the system would not need to be modeled anymore because now it's broke. Okay, so this is what the concept of resonance is all about, and you have these specific properties that have to be all aligned, and basically what happens is this multiplying effect of the amplitude to where everything is resonating, and in any one small change in either the frequency and or the amplitude just makes everything go haywire. And so most people think of resonance when they think of, opera singers shattering glass, or I don't know if you've ever ridden in your car and you've let down the window a bit, and you'll see that the air starts to vibrate back and forth and get really, really loud, and it makes this boom, 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 boom sound like that. And so what's happening is that again, you have resonance happening in the cabin of your car, and you have a little bit of air coming in, but the little bit of air kind of fluctuates back and forth, and it vibrates or oscillates back and forth violently in your cabin, and that's what makes it make that very large, annoying sound. Okay, so anyway, this is the concept of resonance, and one of the things that we want to try to design for whenever we're dealing with spring mass systems is to not have resonance that goes out of control, but when we do have resonance, we want it to be in control, because sometimes depending upon the application, you actually want to experience a gain at a certain frequency and not at others. And so resonance is a way for us to accomplish that. All right, so now that we've talked about case one and the concept of resonance, we're going to go ahead and move on to the part 3 video, and that will entail all of the most of the examples. And I'll probably break the video up into a couple of videos to get all the examples through, because I'll have 6 of them. But we'll try to cover as much as we can without getting too bogged down to the details.